In the quiet vastness of space, a single point of light begins to grow. First, it brightens gently, then suddenly, violently, it explodes into brilliance. For a few brief weeks, it can outshine an entire galaxy. Then, just as quickly, it fades. But what's left behind can shape the universe. This is a supernova, the death of a massive star, and one of the most powerful events the cosmos can produce. It is destruction on a scale almost beyond comprehension. Yet in that destruction, something miraculous happens. Creation. Stars are nuclear furnaces. In their cores, hydrogen fuses into helium, then into heavier and heavier elements: carbon, oxygen, silicon. But even the most massive stars can only go so far. When they begin fusing iron, the process stalls. Iron doesn't release energy when fused, it consumes it. And without the outward pressure of fusion to counteract gravity, the star collapses under its own immense weight. In a matter of seconds, the core crushes down. The outer layers fall inward and then rebound outward in a catastrophic blast, a supernova. The explosion sends shock waves rippling through space, flinging star matter across light years. This blast creates new elements: gold, silver, uranium, forged in the unimaginable pressure and heat. Everything heavier than iron in your body, in our planet, in every ring and circuit was born this way. The calcium in your bones, the iodine in your blood, the gold in your wedding ring, all made in the heart of a dying star. But the story doesn't end with debris. What's left behind may be even stranger. Sometimes, the collapsed core becomes a neutron star, a city-sized object more massive than the sun, with gravity so strong it warps space around it. In rarer cases, the collapse continues until even neutrons can't hold back gravity, and a black hole is born. Supernovae are rare in any single galaxy, but across the universe, they happen constantly, and their impact is enormous. They can trigger new star formation by compressing nearby clouds of gas. They can sterilize nearby planets with radiation. They can shape the arms of galaxies. They can be seen from billions of light years away. In the cosmos, not all endings are quiet. Some end in fire, light, and transformation. And from that final moment, new worlds begin. There are moments in the universe so violent, so sudden, that they release more energy in a few seconds than our sun will emit in its entire lifetime. These are gamma ray bursts, the brightest, most extreme explosions we have ever detected, and they arrive without warning. They come from far-off galaxies, often billions of light years away. For just a few seconds, a flash of high-energy radiation erupts, invisible to human eyes, but blinding to our instruments. When the first ones were discovered in the late 1960s, during military satellite missions meant to monitor nuclear tests, no one knew what they were. The flashes came from deep space, fast, bright, and terrifyingly powerful. We now believe there are two main types of gamma-ray bursts. The first are long-duration bursts, lasting several seconds to a few minutes. These are thought to come from the death of massive stars, specifically when a dying star's core collapses into a black hole and the twin jets of matter are fired from the poles at near light speed. If one of those jets happens to be pointed toward Earth, we witness a gamma-ray burst. The second type, short-duration bursts, last less than 2 seconds and are believed to be caused by the merger of two neutron stars, a collision so dense and energetic that it creates both gravitational waves and intense bursts of gamma radiation. Either way, the result is the same: a flash of energy that can fry electronics on satellites, distort the Earth's ionosphere, and leave scientists scrambling to understand the aftermath. We've even asked the question, could a gamma ray burst end life on Earth? It's not just science fiction. If one occurred close enough, within a few thousand light years, and was directed at us, the radiation could strip away our ozone layer, exposing the surface to harmful ultraviolet light and triggering a global extinction event. Some researchers even speculate that ancient gamma-ray bursts may have played a role in past mass extinctions. But they're also signals, cosmic sirens announcing the formation of black holes, the collisions of stellar remnants, and the limits of energy release in nature. They allow us to peer into the early universe, since many of the most distant ones come from the first generations of stars. Gamma-ray bursts are not just powerful, they are precise, focused beams of annihilation, narrow, fast, and final. And every time one appears, we are reminded how fragile light and life truly is. We tend to think of planets as stable, permanent things, solid ground, predictable orbits, steady rotations. But in the history of the cosmos, planetary collisions are not rare events. They're foundational ones. Planets are not born peacefully. They are built in fire, shattered by violence, and shaped again and again by impact. Early in a star system's life, chaos rules. Dozens, even hundreds, of protoplanets spiral through unstable orbits, colliding, merging, or tearing each other apart. Gravity pulls them together, but when their paths cross, the result is often cataclysmic. Imagine two planetary bodies, each the size of Earth or Mars, colliding at tens of kilometers per second. The force released is trillions of nuclear bombs, enough to melt crusts, vaporize atmospheres, and fling entire mountains into orbit. The result isn't just destruction, it's reformation. Astronomers now believe that many of the planets we observe, including those in our own solar system, bear the scars of ancient collisions. Mercury's oversized iron core may be the result of a massive impact that stripped away its outer layers. Uranus is tipped on its side, possibly due to a glancing planetary blow. And Earth may owe its very identity to one. We'll return to that specific collision in the next chapter. But planetary smash-ups happen elsewhere too, and sometimes we witness them indirectly. In distant star systems, telescopes like Kepler and TESS have caught glimpses of fresh debris disks, warm clouds of dust that suddenly appear around young stars. Those may be the aftermath of planetary collisions, a signal that two worlds just crashed into one another, their fragments now glowing in infrared light as they cool. Some systems even show pulses of strange light or unusual chemical signatures, suggesting molten surfaces, ejected cores, or atmosphere-stripping impacts. These are not just theoretical. They're observable consequences of a chaotic process that still echoes across the galaxy. Collisions can also explain planetary oddities, extreme orbits, tilted axes, missing atmospheres. They're a reminder that planets are not sculpted gently. They're hammered into being, one crash at a time. And even after billions of years, it never fully stops. In a dynamic universe, peace is temporary, but from every collision, something new is forged. Look up at the moon, and you're seeing the aftermath of a cataclysm. A world torn apart. A planet changed forever. Because our moon, quiet, familiar, serene, was born in fire. And it may have been the result of the most important impact in Earth's history. The leading theory, known as the giant impact hypothesis, suggests that early Earth didn't always have a moon. In the turbulent youth of the solar system, Earth was still forming, young, molten, and frequently bombarded. Then one day, a Mars-sized object, a rogue protoplanet we call Theia, struck Earth at a glancing angle. It wasn't a head-on crash. It was worse. A slow-motion, planet-shattering blow. The force was enough to vaporize vast sections of Earth's outer layers and completely destroy Theia. The impact ejected an enormous plume of molten rock and metal into orbit, forming a glowing ring of debris. Over time, maybe months, maybe years, that ring coalesced into the moon. But the consequences didn't stop there. That impact likely tilted Earth's axis, giving us seasons. It may have accelerated Earth's rotation, shortening our days. And most importantly, the newly formed moon began to stabilize Earth's wobble, preventing wild climate swings and chaotic precession. Without the moon, Earth's climate might have fluctuated too violently for life to ever gain a foothold. Chemical analysis of lunar rocks supports this origin story. The moon's composition is almost identical to Earth's outer layers, suggesting a shared origin, but with key differences that imply extreme heat and mixing. No other theory explains those observations as clearly as a massive collision. And Theia, it's gone, merged with Earth, scattered into space, or perhaps lingering deep within our planet. Some scientists even speculate that unusual structures near Earth's core, dense, continent-sized blobs, could be remnants of Theia's mantle, still buried inside us after 4 billion years. It's poetic in a way. The moon that lights our night sky may be the ghost of a lost world, the still glowing memory of the day Earth became what it is. From destruction came balance, from chaos came orbit, and from one terrible impact came home. In July 1994, something extraordinary happened, something we had never seen before. For the first time in human history, we watched as a celestial body collided with a planet in real time. The object was a comet. The target was Jupiter, and the impact left scars big enough to swallow Earth whole. The comet was called Shoemaker-Levy 9, a fragile traveler that had been captured by Jupiter's immense gravity years earlier. Instead of escaping, it entered a decaying orbit, one that pulled it closer and closer until the tidal forces of Jupiter's gravitational field tore it apart. The result was a string of icy fragments, lined up like pearls in space, each tens of kilometers wide. Astronomers around the world turned their telescopes toward Jupiter, uncertain of what would happen next. Then, one by one, the fragments began to strike. Over the course of several days, they slammed into Jupiter's upper atmosphere at more than 200,000 kilometers per hour, releasing energy equivalent to millions of nuclear bombs. The impacts sent plumes of gas rising 3,000 kilometers above the cloud tops and left dark scars, bruise-like blemishes, visible even in amateur telescopes. But beyond the spectacle, Shoemaker-Levy 9 reminded us of something more profound. Jupiter protects us. Because of its massive size and powerful gravity, Jupiter acts as a kind of cosmic vacuum cleaner, sweeping up comets, asteroids, and space debris that might otherwise strike the inner planets, including Earth. In many simulations of solar system dynamics, Jupiter is the great deflector, pulling dangerous objects away or catching them in its own atmosphere. Without Jupiter, Earth might have suffered many more catastrophic impacts over its history. Some scientists refer to Jupiter as a gravitational shield, though it's not perfect. Its presence increases the complexity of object trajectories, and sometimes even sends objects inward. But overall, the gas giant plays a vital role in reducing the number of high-speed intruders that reach our neighborhood. Shoemaker Levy 9 was a rare event, but it served as a warning and a gift. It showed us that planetary impacts are still happening, even now. It reminded us how fragile our planet truly is, and it revealed that in the darkness of space, we are not entirely alone. Sometimes the giants take the hit for us. 66 million years ago, Earth was full of life. Dinosaurs roamed vast continents, flying reptiles soared through the skies, and lush forests stretched across the land. Then, in a moment, just one terrible instant, everything changed. A rock, roughly 10 kilometers wide, slammed into what is now the Yucatan Peninsula in Mexico. It struck with the force of more than 1 billion nuclear bombs, traveling faster than a bullet, and released more energy than all the world's volcanoes could produce in 1 million years. This was the Chicxulub impact, one of the most devastating events in Earth's history and the most famous mass extinction trigger ever discovered. The immediate effects were apocalyptic. The impact blasted a crater more than 150 kilometers wide and over 20 kilometers deep. Rock vaporized. Oceans boiled. Firestorms swept across continents. Earthquakes circled the globe. And worse still, the collision hurled billions of tons of sulfur, ash, and debris into the atmosphere, blotting out the sun. What followed was not just fire, it was darkness. Temperatures plummeted. Photosynthesis stopped. Plants died. Then the animals that fed on them. An estimated 75% of all life on Earth vanished, including every non-avian dinosaur. But from that extinction came transformation. The disappearance of the dominant species opened evolutionary paths that had been blocked for millions of years. Small mammals, once insignificant in the shadow of giants, began to diversify. Among them were the ancestors of primates, and eventually of us. The evidence for this story is now overwhelming. The iridium layer found in rocks all over the world, an element rare on Earth but common in asteroids. The Chicxulub crater, still visible beneath layers of sediment. The fossil record, showing a sudden global collapse of ecosystems at the end of the Cretaceous. And so, the sky that brought death also brought renewal. The Chicxulub impact is a reminder of Earth's vulnerability and its resilience, that in a single moment the course of life can shift, and that every living thing today, in some way, carries the legacy of that ancient fire. The age of dinosaurs ended not with a whimper, but with a flash, and in the ashes, the age of humans began. Not all cosmic catastrophes come from the sky. Some rise from deep within the earth in events just as devastating, just as transformative, but slower, darker, and longer lasting. One such event occurred around 74,000 years ago in what is now Sumatras, Indonesia. It was the eruption of a supervolcano called Toba, and it may have nearly wiped us out. The Toba supereruption is believed to be the largest volcanic eruption on Earth in the last 2 million years. It expelled an estimated 2,800 cubic kilometers of material, blanketing parts of Southeast Asia in ash and launching aerosols high into the stratosphere. That ash fell as far as India and East Africa. The explosion was thousands of times more powerful than any eruption in recorded history, a VEI8 event, the highest possible on the Volcanic Explosivity Index. But the ash cloud was only part of the disaster. Far more dangerous was what followed: a volcanic winter. As fine ash and sulfur dioxide spread across the planet, they blocked sunlight, cooled global temperatures, and disrupted rainfall patterns. Some models suggest that Earth's average temperature may have dropped by as much as 3 to 5 degrees Celsius, with even greater local declines. Crops didn't fail. They hadn't been invented yet, but ecosystems did. Plants withered, animal populations crashed, and with them, early human communities. Genetic evidence hints at something chilling. Studies of mitochondrial DNA suggest that modern humans passed through an extreme population bottleneck around this time. Possibly as few as a few thousand individuals survived globally. We don't know for certain that Toba caused this, but the timing aligns. It's possible that our entire species was nearly erased, not by asteroid or war, but by a volcano half a world away. And yet, we survived. The bottleneck may have shaped the genetic diversity of modern humans. Some researchers suggest it fostered closer cooperation, migration, and innovation. In the millennia following Toba, humans spread rapidly across Africa and beyond. Whether driven by hardship or opportunity, the species endured and grew. Toba reminds us that extinction isn't always sudden. Sometimes it comes as a slow, cold shadow that lingers for years. And survival doesn't always roar. Sometimes it whispers. In that whisper, humanity found its voice. The sun, for all its warmth and constancy, hides a violent heart. Beneath its golden surface, magnetic fields twist and snap like cosmic whips, releasing titanic eruptions of energy and charged particles into space. Most of the time, these outbursts pass unnoticed, but sometimes they hit Earth, and when they do, the sky lights up and our fragile technology trembles. The most powerful such event ever recorded happened in 1859. It's known today as the Carrington event, named after British astronomer Richard Carrington, who was observing the sun that day when he saw something strange, a sudden blinding flash of light from a sunspot. What we now know was a solar flare, the visible start of a coronal mass ejection. Just 17 hours later, and incredibly fast transit times, the storm hit Earth. What followed was unprecedented. The night skies erupted in auroras so bright they were seen as far south as the Caribbean. In the northern United States, people could read newspapers at midnight by the shimmering green and red glow. Telegraph systems, the cutting-edge technology of the time, failed spectacularly. Sparks flew from telegraph machines. Operators were shocked, and some systems continued to send messages even after being disconnected from their power sources. This was not just a beautiful light show. It was a planet-wide electrical event. If a storm of this magnitude were to happen today, the results would be far more devastating. Power grids could collapse, satellites could be fried, GPS, internet, and communication networks could be crippled. Flights, navigation, banking systems, all of modern life would be vulnerable, and the risk is not theoretical. In 1989, a solar storm far weaker than the Carrington event knocked out the power grid in Quebec, plunging millions into darkness. In 2012, Earth narrowly missed a Carrington-class storm. A massive CME erupted from the Sun and passed through Earth's orbital path, but Earth had just moved on. Scientists monitor the Sun constantly now. Spacecraft like SOHO and the Parker Solar Probe track solar activity, giving us hours, sometimes days, of warning, but we can't stop it. We can only brace. The Carrington event was a reminder that our star is not tame. It giveth warmth, light, energy, but it also threatens. And someday, perhaps soon, the sky may flare again, not with beauty, but with warning. From the deepest reaches of space, invisible messengers arrive, tiny high-energy particles traveling at nearly the speed of light. They pass silently through magnetic fields, slice through planetary atmospheres, and sometimes strike us directly. These are cosmic rays, and though they are smaller than atoms, their impact can be enormous, even written into our DNA. Cosmic rays are mostly protons, fragments of atoms accelerated to incredible energies by powerful events, supernovae, active galactic nuclei, and possibly even more exotic sources like colliding black holes. They don't come in steady streams, but in bursts and waves, shaped by solar activity and the motion of our solar system through the galaxy. Most are harmless. Earth's magnetic field and atmosphere protect us, shielding the surface from the highest doses. But a small fraction gets through. They interact with the atoms in our atmosphere, triggering particle showers, cascades of secondary particles that rain down, some reaching the ground and even our cells. And sometimes these particles hit DNA. One impact can break chemical bonds, alter a sequence, or flip a genetic switch. Most of the time, our cells repair the damage, but occasionally, A cosmic ray triggers a mutation, a tiny random change that becomes part of the genetic code. Some mutations are neutral, some are harmful, but some, by chance, are useful. This is one of the quietest, strangest truths about cosmic evolution. Mutation drives change, and cosmic radiation is one of the engines behind it. Over millions of years, cosmic rays may have contributed to the rise of new traits, the fall of old ones, and the gradual transformation of species. They are not the only cause of mutation, but they are a cosmic contributor to Earth's biology, constantly delivering randomness into the delicate balance of life. And during periods of intense stellar activity, like when a nearby star explodes in a supernova, the dose can rise. Some researchers believe past extinction events or bursts of evolutionary change may have been influenced by increased cosmic radiation, disrupting ecosystems and accelerating mutation rates. For astronauts beyond Earth's protective shield, the risk is even greater. Cosmic rays can damage tissue, increase cancer risk, and pose a major challenge to deep space missions. But here on Earth, they continue to fall, unseen, unfelt, and constant. Cosmic static, tapping on the glass of our biology. Tiny accidents, seeded from the stars, and within those accidents, evolution. Most stars die quietly, some go out in brilliant explosions, but a few, the most extreme, the most exotic, do something else entirely. They shake, not like a tremble or a ripple, but a deep internal fracture that sends energy roaring across the galaxy. These are starquakes, and they happen on some of the strangest objects in the universe, magnetars. A magnetar is a type of neutron star, the collapsed core of a massive star that died in a supernova. It's only about 20 kilometers across, the size of a city, but it can weigh more than our sun. Its gravity is so intense that atoms are crushed. Its crust is ultra-dense, and the whole star is wrapped in a magnetic field a quadrillion times stronger than Earth's. It's that magnetic field that sets a magnetar apart. Twisting, snapping, constantly shifting under pressure, it distorts the surface of the star until, one day, the crust gives way. And when that happens, a starquake erupts. The energy released can be enormous. In one case, detected in 2004 from a magnetar called SGR 1806-20, a burst of gamma rays reached Earth from 50,000 light-years away, and for a fraction of a second, it outshone the entire Milky Way. Satellites in orbit were overwhelmed. Earth's upper atmosphere expanded under the sudden wave of energy, and yet the magnetar barely flinched. A starquake is caused when the immense magnetic forces inside the magnetar twist and shear its rigid crust, not unlike tectonic plates on Earth, but on a cosmic scale. The crust shifts just a few centimeters, and the result is the energy equivalent of 10 to the power of 39 ergs. That's more than our sun will emit in 100,000 years, released in a fraction of a second. These bursts aren't just destructive, they're also informative. They allow us to study the interiors of neutron stars, probe the limits of matter, and even test the laws of physics under conditions we could never reproduce on Earth. Magnetars don't last long in cosmic terms, just tens of thousands of years. But in that brief lifetime, they unleash some of the most violent events in the universe. They are not explosions. They are not collisions. They are something rarer, a star breaking itself from the inside out. And in that fracture, the cosmos listens. At the end of a massive star's life, a quiet battle unfolds. Gravity pulling inward, nuclear fusion pushing outward. For millions of years, the balance holds. But when the fuel runs out, when the core can no longer resist the weight above it, the balance shatters. The star collapses, not gently, not slowly, but catastrophically. And in that collapse, the universe creates one of its most mysterious and terrifying objects, a black hole. It doesn't start with darkness. It starts with light. As the core implodes, a shockwave rips through the star, producing a supernova, a flash so bright it can be seen across galaxies. But behind the light, something stranger is forming. If the collapsing core has enough mass, typically more than 3 times that of our sun, nothing can stop the fall. Not atomic pressure, not neutron resistance. The collapse continues until matter is crushed into a single, infinitely dense point, a singularity wrapped in an event horizon from which not even light can escape. This is the birth of a stellar mass black hole. For years, black holes were theoretical, strange solutions to Einstein's equations. But now we see their fingerprints everywhere, in binary star systems, where one invisible companion pulls gas from its neighbor, heating it until it glows in X-rays. In gravitational waves, ripples in space-time created when black holes merge. In the motions of stars whipping around unseen centers, orbiting emptiness. The collapse into a black hole is not just an end, it's a transformation. The star's identity vanishes. Time and space are warped beyond recognition. From the outside, it may appear frozen, the final collapse slowed by relativity. But inside, the fall is absolute. Some stars leave behind white dwarfs, others neutron stars. But the biggest go silent, not cold, but invisible, not dead, but unreachable. And yet, black holes are not cosmic voids of destruction. They are engines. They shape galaxies, power quasars, bend light, and hold time itself hostage. The collapse of a single star can become the anchor for entire star systems, guiding matter through gravity, not heat. When a star collapses into a black hole, it doesn't simply disappear. It becomes a new kind of presence, quiet, permanent, and strange. A place where the universe folds in on itself and dares us to understand. Not all stars end in quiet ashes. Some die in pairs, locked in slow, spiraling dances that last for billions of years. And when the moment comes, when two stellar corpses finally collide, the result is one of the most precise and powerful explosions in the cosmos, a Type Ia supernova. These supernovas don't come from massive stars collapsing under their own weight. They're born from smaller stars, the kind that live long, stable lives and die as white dwarfs, cooling embers of stellar evolution. A white dwarf is incredibly dense, about the size of Earth, but with the mass of the Sun. It has no fusion left in its core. It simply radiates heat, slowly fading away. But if a white dwarf is in a binary system, especially one with another white dwarf, the story can take a dramatic turn. Over time, the two dead stars spiral closer together. Their gravitational dance grows tighter, energy radiates away, and eventually they collide. When that happens, and the mass of the combined object crosses a critical threshold, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, something astonishing happens. The pressure and temperature rise so rapidly that the carbon and oxygen inside the white dwarf ignite in a runaway fusion reaction. But unlike a normal star, which burns gradually, this reaction consumes the entire star in seconds. There is no core collapse, no remnant, just a thermonuclear explosion that tears the star apart from within. The result is a Type Ia supernova, bright, violent, and astonishingly uniform. And that's what makes them so valuable, because these explosions occur at a predictable brightness. They serve as standard candles, cosmic mile markers. By comparing how bright they appear to how bright we know they truly are, astronomers can calculate distances across the universe. It was through observations of Type Ia supernovae that scientists discovered the accelerating expansion of the universe, leading to the theory of dark energy. So from the quiet death of two small stars comes a burst of light that reshapes our understanding of the cosmos. In that moment, time and distance reveal themselves. Two long dead stars collide, and the universe blinks, just once, brilliantly. And in that blink, we learn how far we've come, and how fast everything is still moving apart. From a distance, galaxies look eternal, glowing spirals floating in darkness, elegant and serene. But galaxies are not fixed. They move. And when they meet, they don't politely pass by. They collide. They merge, they tear themselves apart, and in doing so, they reshape the universe on the grandest scale imaginable. Our own galaxy, the Milky Way, is not immune. In fact, it's already on a slow-motion collision course with its nearest large neighbor, the Andromeda Galaxy, 2 million light-years away and getting closer every second. The two galaxies are expected to collide in about 4.5 billion years. It won't be a crash in the traditional sense. The stars inside each galaxy are so far apart that direct collisions between them will be rare. But gravity will pull, twist, and warp both galaxies, ripping away spiral arms, flinging stars into new orbits, and eventually merging the two into a single, massive elliptical galaxy, sometimes referred to as Milkomeda. This isn't a violent end for stars, but it is a cosmic upheaval. Supermassive black holes at the centers of both galaxies will spiral together and merge, sending out gravitational waves across the universe. Gas clouds will be compressed, triggering intense bursts of new star formation, starbursts that briefly light up the merging system. Some stars may be ejected entirely, thrown into intergalactic space at extreme speeds. Galaxy collisions are common in the universe. In fact, they're part of how galaxies grow. Many of the largest galaxies we see today are the result of past mergers, stitched together by the gravity of smaller systems long absorbed. And they don't just change shape, they change fate. Collisions can activate dormant black holes, ignite quasars, and alter the structure of entire galactic clusters. We've observed these events in every stage, from first contact to warped mid-mergers to fully blended remnants. The Hubble and James Webb Space Telescopes have captured snapshots of these titanic encounters across billions of years, each one telling part of the story of how galaxies live and die. And when the Milky Way and Andromeda finally meet, Earth may still be here. Our sky will transform, filling with streams of new stars, warped arms, and glowing gas. For 1 billion years, the night will shift, shimmer, and change. And though we may not survive to see it, the galaxy we call home will be reborn, not destroyed, but transformed. Not an end, but a new beginning written in stars. Most black holes stay anchored, nestled at the centers of galaxies, or quietly orbiting as the remnants of collapsed stars. But not all of them follow the rules. Some black holes are wanderers, drifting, invisible, alone. These are rogue black holes, and they may be quietly moving through the cosmos, including our own galaxy, right now. A rogue black hole is born when violence severs its ties. Sometimes it's ejected during the chaotic merger of two galaxies, flung outward by gravitational recoil after two supermassive black holes collide and merge. Other times, it's the result of a failed stellar core collapse, where the explosion kicks the newborn black hole with enough velocity to escape its stellar neighborhood, or even the entire galaxy. Once loose, a rogue black hole moves silently through space. It emits no light, no heat, no radiation, unless it happens to pass through a region with gas or dust to devour. Most of the time, it doesn't. It is simply darkness in motion, a gravity well wrapped in silence. Detecting such objects is notoriously difficult. They don't glow, they don't cast shadows, but they do bend light. In 2022, astronomers reported one of the most promising candidates yet, a potential stellar mass black hole drifting through the Milky Way, detected via gravitational microlensing. When the black hole's gravity briefly magnified the light of a background star as it passed in front of it. This was a subtle, delicate observation, but a powerful proof of concept. It means we can, with patience and precision, begin to track the invisible. Rogue black holes may be far more common than we think. Some estimates suggest that millions of them could be drifting through the Milky Way alone, each a ghost of a once living star. Most will never come close to a planet or star, but if one did, the results would be catastrophic. Its gravity could disrupt orbits, pull apart moons, or even swallow entire solar systems, quietly, efficiently, without a sound. And yet, most will never touch anything at all. They roam the galaxy not as predators, but as relics, evidence of the chaos that shaped the early universe. They are the shadows that move, and somewhere out there between stars, they are still drifting, cold, undetected, and waiting. In late 2019, something strange happened in the sky. Betelgeuse, the red supergiant that blazes bright in the shoulder of Orion, began to fade. Not a little, but a lot. Over just a few weeks, it dimmed by more than 60%, visibly changing one of the most familiar constellations in the night sky. For a moment, the astronomical world held its breath. Was this the beginning of the end? Was Betelgeuse one of the largest, most unstable stars we can see, about to explode in a supernova? It wasn't, at least not yet. But the event, now known as the Great Dimming, was a powerful reminder of how close and how volatile some stellar catastrophes truly are. Betelgeuse is enormous. If placed in the center of our solar system, it would stretch beyond the orbit of Jupiter. It's nearing the end of its life, fusing heavier elements in its core and preparing eventually for collapse. That much we've long known. But what we hadn't seen until 2019 was just how dramatically its outer layers could shift in real time. At first, the dimming was a mystery. Telescopes around the world focused in, and multiple theories emerged. One suggested a massive star spot, a cool patch on the surface that temporarily reduced the brightness. Another pointed to a sudden ejection of material, a belch of gas and dust from the star's outer layers that cooled and condensed into a giant dust cloud, blocking our view from Earth. Eventually, the dust explanation gained the most support. Images from the Very Large Telescope in Chile even showed changes in Betelgeuse's shape, a visible distortion caused by the asymmetrical outflow of matter. In other words, the star had coughed. And that cough taught us something. It showed that stars don't just fade in the abstract span of eons. Sometimes they change before our eyes. Betelgeuse is expected to go supernova within the next 100,000 years, a blink in cosmic time. When it does, it will briefly become as bright as the full moon and be visible in daylight, but no one knows when. The Great Dimming was not the final act, but perhaps a rehearsal, a warning flicker from a star nearing the end of its script. And now, every night it rises, we wonder, is tonight the night Betelgeuse goes dark forever? In the vast cold clouds between the stars, places we call nebulae, the seeds of suns are waiting. These star-forming regions are quiet to the eye, but not to the universe. Inside them, gravity works slowly and patiently, pulling gas and dust together until something ignites. And once a single star is born, it can set off a chain reaction, turning a silent cloud into a cosmic factory of fire. It begins with a collapse. Somewhere in the molecular cloud, a pocket of gas grows dense enough to trigger gravitational infall. As it shrinks, it heats up. A protostar is born. And when fusion finally begins, when hydrogen becomes helium in its core, the star erupts with energy and light. But its birth doesn't just end the story of its own formation. It changes the entire neighborhood. Young, massive stars in particular, O and B-type stars, emit intense radiation and powerful stellar winds. They blow bubbles into the surrounding cloud, pushing gas away, carving out cavities. These winds compress the edges of nearby clumps of gas, triggering new collapses, new stars, and new outbursts. It's a feedback loop, a fire that spreads. In some cases, a massive star dies quickly in a supernova, and the explosion slams into the nearby cloud, triggering even more star formation. The shock wave acts like a hammer, compressing matter into filaments and cores. This cascading process is how entire clusters of stars are born, not one at a time, but in waves, one birth igniting the next. Astronomers have observed these phenomena in regions like the Orion Nebula, the Carina Nebula, and NGC 346. These glowing clouds teem with infant stars, some still wrapped in disks of material, forming planets. In infrared and radio wavelengths, we can see the signature of the collapse, the outflows, the heat, the whole cycle in motion. And sometimes, a single massive star, just one, can change everything. Its presence accelerates or halts star formation across light years. It can sculpt a region for millions of years, creating beauty and violence in equal measure. Star factories are not gentle nurseries. They are shaped by interstellar cause and effect, by pressure and fire, by the fragile balance between collapse and destruction. And in the chaos, suns are born, not alone, but together, in a galactic chain reaction that will light the sky for ages to come. Not all stars stay where they're born. Some are ejected, hurled from the centers of galaxies, flung across the void at breakneck speeds, cast out by forces so immense that they escape not just their stellar neighborhoods, but sometimes their entire galaxy. These are hypervelocity stars, and they are the fastest rogue travelers in the universe. First predicted in theory, then discovered in the early 2000s, hypervelocity stars are real and rare. While most stars orbit calmly within the gravitational pull of their galaxy, a hypervelocity star breaks free, traveling at speeds of hundreds or even thousands of kilometers per second. Some move so fast they exceed the escape velocity of the Milky Way, destined to wander intergalactic space for eternity. But what could fling something as massive as a star? One of the most likely mechanisms involves a close encounter with a supermassive black hole. Imagine a binary star system, two stars orbiting one another, drifting too close to the monster lurking at the center of the galaxy. As the pair nears the black hole, tidal forces tear them apart. One star is captured, spiraling inward toward the black hole, and the other is catapulted outward, its orbit converted into a slingshot of unimaginable speed. This gravitational three-body interaction is like a cosmic billiards game, with the black hole breaking the pair and launching one ball into deep space. But that's not the only path to hypervelocity. Some stars may be flung outward during galactic collisions, such as the future merger between the Milky Way and Andromeda. Others could be ejected from dense stellar clusters, or by the collapse of massive systems where gravitational instability turns chaos into acceleration. Observations have found hypervelocity stars moving away from the galactic center and even from the Large Magellanic Cloud, suggesting multiple origins. Some of these stars are massive and young, burning bright and hot, destined to live short, fast lives far from where they began. They carry more than just speed. They carry stories of violence, of disruption, of cosmic dynamics writ large. They show us that even stars, those great anchors of the night sky, can be dislodged and flung like sparks from a galactic forge. And somewhere out there, in the silence between galaxies, those sparks are still flying. Some stars are born together, twin lights orbiting each other in an elegant gravitational dance. These binary systems are common in the universe, and for much of their lives, the stars coexist peacefully, orbiting a shared center of mass. But sometimes, the balance breaks. One star begins to swell, or collapse, or steal, and what begins as a partnership becomes a slow-motion catastrophe, a death spiral. This deadly dance can take many forms, but the most dramatic begin when the stars grow old. As one star exhausts its nuclear fuel, it expands into a red giant, spilling its outer layers into space. If its companion is close enough, it begins to accrete that matter, pulling it in with its gravity, gaining mass and spinning faster. A stream of gas flows from one star to the other, forming a glowing accretion disk, often lighting up in X-rays and ultraviolet. The system becomes unstable. If the receiving star is a white dwarf and it gains too much material too quickly, the pressure can ignite runaway fusion on its surface, triggering a nova. Or if the mass exceeds a critical limit, the entire white dwarf can detonate in a Type Ia supernova, obliterating itself and potentially its partner. In other cases, both stars may be compact remnants, two white dwarfs, or two neutron stars, or even black holes. Over millions or billions of years, they lose energy by radiating gravitational waves, spiraling closer and closer until finally they collide. The final seconds are explosive. Two neutron stars merging can create a kilonova, a flash of light and heavy elements, including gold and platinum, hurled into the cosmos. Two black holes merging ripple space-time itself, sending gravitational waves that stretch and compress everything in their path. We've detected these signals, heard the echoes of their final orbits through detectors like LIGO and VIRGO. Sometimes, the stars don't wait for collapse. One may simply spiral into the other, swallowed whole. In rare cases, we may witness a luminous red nova, a brilliant flash as the stars merge into one. Binary star systems show us that death isn't always sudden. Sometimes it's a long descent, a slow spiral through heat and hunger, until at last there is only one, a survivor left spinning, glowing, or gone. And in their fall, these stars tell a larger story, that even the most beautiful dances can end in collision. Deep beneath Earth's surface, molten metal flows like a slow, swirling river, a churning ocean of iron and nickel at the heart of our planet. That motion generates Earth's magnetic field, the invisible shield that protects us from solar wind, cosmic rays, and radiation. But this shield is not fixed. It drifts, it wobbles, and sometimes, in a moment of planetary instability, it flips. These are geomagnetic reversals, times when Earth's magnetic poles switch places. North becomes south. Compass needles would point the wrong way, and for a brief geological moment, the magnetic field itself becomes chaotic, weakening, or even fragmenting. Reversals are not theoretical. They've happened many times throughout Earth's history. roughly every few 100,000 years, though not on a precise schedule. The most recent complete flip, known as the Brunhes-Matuyama reversal, occurred about 780,000 years ago. Since then, the field has wandered, fluctuated, and weakened, but not yet reversed again. When a reversal happens, it doesn't occur overnight. The process can take hundreds to thousands of years, with the magnetic field weakening significantly before the flip finalizes. During this time, Earth's magnetic protection is compromised. More solar radiation reaches the surface. Auroras become more frequent and widespread, even at the equator. Satellites and communication systems, if they had existed during past reversals, would have been at serious risk. But the real concern isn't aesthetic. A weaker magnetic field means greater exposure to space radiation, which can damage the ozone layer, disrupt animal navigation, and affect electrical infrastructure. During a transition, Earth might experience multiple magnetic poles at once, scattered across the planet, a magnetic map in chaos. Some scientists believe we've already entered the early stages of a reversal. The South Atlantic Anomaly, a region where Earth's magnetic field is unusually weak, has been growing and shifting. The magnetic North Pole has also been drifting faster than expected, moving from Canada toward Siberia. Still, reversals are not extinction events. Life has survived many of them, but they are planetary scale disruptions recorded in rocks, sediments, and even ancient pottery. And when the next one comes, whether in a century or 1,000 years, it will remind us that Earth's core, though hidden, never rests. In the stillness of continents, a silent revolution brews, not of fire or impact, but of magnetism. And when the compass turns, the planet will remember. This world spins, not just on its axis, but on its field. For most of human history, asteroid impacts were the stuff of myth or mystery. Fire from the sky, gods casting stones, unexplained craters. But today, we know better. We know the scars on Earth's surface. We know the story of the dinosaurs' end. And more importantly, we know that it could happen again. But for the first time in history, we're doing something about it. NASA, along with international partners, has been developing a strategy to defend Earth from hazardous near-Earth objects, NEOs, asteroids and comets whose orbits bring them close to our planet. The goal is simple in theory, but massive in scope. Find the threats before they find us, and if necessary, stop them. The first step is detection. NASA's Center for Near-Earth Object Studies, CNEOS, tracks tens of thousands of objects using ground-based telescopes and space observatories. Projects like NEOW, ISE scan the skies in infrared, detecting dark asteroids invisible to optical telescopes. But even with these efforts, we still haven't found them all. especially smaller ones, like the 50 to 140 meter objects that could devastate a city. That's why NASA is preparing to launch a new mission, NEO Surveyor, a dedicated space telescope that will search specifically for dangerous asteroids. It's designed to find 90% of near-Earth objects larger than 140 meters, the current congressional mandate, within the next decade. But detection is only part of the equation. The bigger question is, what do we do if we find one? In 2022, NASA made history with the DART mission, the Double Asteroid Redirection Test. A spacecraft deliberately slammed into a small asteroid called Dimorphos, successfully changing its orbit. It was the first real-world test of kinetic impact deflection, proving that, with enough warning time, we can alter the course of a space rock. Other options are being explored too. Gravity tractors, where a spacecraft slowly tugs an asteroid using its own gravitational pull, laser ablation, using heat to gently push an object off course, even nuclear detonations, though that remains a last resort. Planetary defense is no longer science fiction. It's engineering, strategy, and time. And it's happening now. Because space is not empty. It's full of ancient fragments left over from the birth of the solar system. And while most will miss us, it only takes one. So we watch, we prepare, and for the first time in Earth's long, scarred history, the planet is learning how to defend itself.